LangGraph is an extension of LangChain that builds on top of LangChain's foundation to give additional features. And you might be wondering, wait, why not just use LangChain? Why are you making this more complicated for me? Well, that's good because complicated is the perfect word to capture the essence of understanding the true difference between LangChain and LangGraph. So you might be asking the question, what's the true difference between LangChain and LangGraph? If you're building a simple chatbot that answers customers' questions based on companies' policies, LangChain will most likely suffice in getting the job done, since they're built for simple and deterministic tasks. However, some business requirements go way beyond a simple company chatbot. Let's say you're asked to build a deep research assistant software for your company that helps you go through a large swath of information gathered from various sources. In this case, the use case is a lot more complicated than a chatbot, and using LangGraph will start to make more and more sense. One way to look at it is the threshold from changing from LangChain to LangGraph really comes down to a component that's called StateGraph. Essentially, when you use StateGraph, you have the ability to add what's called nodes and edges. A node is an individual unit of computation. So think of a function that you can call. And an edge is a transition between these nodes that can either pass through or be conditional. So let's go back to the deep research assistant as an example to understand the difference with a little bit more granularity. So let's say the business requirements for the deep research assistant was to first browse the web, then find relevant details about a given topic, and let's say the research requirement was about Tesla's earnings call. And then the assistant needs to read and comprehend all news sources from blogs, forums, research papers, and social media, and finally decide if the information contained is trustworthy and useful. And each source of information needs to surpass 75% in order for it to be deemed as trustworthy. And the final step for the assistant is to then gather all the credible data and build a report. In traditional software development, you not only have to write code that first fetches a set of links using a search engine API, second, loop through these links manually, third, scrape the content and feed it to a large language model, four, evaluate the score for each source, and five, check the score and only use sources that surpasses 75%, and six, analyze and store these facts into a report. You not only have to write all of these code individually, but also orchestrate the sequence of how these code will run in order to maintain them. Now with LangGraph, the steps look a little bit more streamlined. The entire process can be run using a graph, where each node is responsible for a very specific task, and each edge determines the flow or execution steps. So in our case, we need to create nodes for the following tasks. First, a node to search and gather sources. Second, a node to scrap and clean content. Third, a node to evaluate trustworthiness using an LLM. Four, a node to extract factual statements from the sources. And five, a node that generates a report. And once all these nodes and edges are configured and compiled, LangGraph will orchestrate them by executing them based on how it's configured. So for a deep research assistant, the graph will look something like this, where you have the starting node that serves as the entry point, and all the nodes and edges that do individual tasks, and finally an end node that terminates the workflow. Now what makes LangGraph special is what's called StateGraph, meaning they all have a shared state. A state essentially serves as a persistent memory for the workflow to store pertinent information at all different parts of the workflow. So in our case of deep research assistant, the state might look something like this. Class research state, topic that's a string, remaining URLs, which is a list of strings, current URL, which is an optional string, content, which is an optional string, current score, which is an optional integer, and facts, which is a list of strings. So now that we have the state and the graph, let's actually see how LangGraph would execute them step by step. The topic in this case will be Tesla's earnings call. So the first node that gathers news sources and sites looks at the topic state and gathers information about Tesla's earnings call. It'll then populate all the results it got to a state variable called remaining URLs. The next node will scrape and clean the content from each URL and populate the state variable called current URL and the content that's within it so that it can be further processed by a later node. The next node will evaluate the trustiness of the information that was gathered and make sure that it scores it properly, appends it to the state variable called current score. And once all the URLs are scraped and scored properly, it'll then go to the next node that extract factual statements from all these sources. And finally, the last node will generate a report based on the facts that are given within the state graph. So as you can see, state graph plays a critical role in persisting information within the workflow, and it's an important piece in orchestrating of the workflow. And it's through this nature of graph part in LangGraph that provides additional features like loops, conditional branching, and state management that helps you build a more complicated application than what LangChain might offer out of the box. As enterprise adoption of agentic software grows, tools like LangChain are a natural progression towards workflow automation, and understanding when and how to use LangGraph can help you solve very interesting problems without having to write unnecessary code. mode. LangGraph really just helps you focus on architecture and problem solving rather than how to implement the orchestration and how each component should run. Now that we've covered the conceptual elements of LangGraph, let's look at how it looks like on a practical level. To better understand this, we can look over at this lab specifically geared towards how to use LangGraph. Alright, now let's do some hands-on work and actually build this research assistant together. Go ahead and copy the installation command from the first section. We're setting up our complete LangGraph stack here. This includes LangGraph itself, LangChain core packages, state management tools, and most importantly, DuckDuckGo for free web searching. No API keys needed for that one, which is perfect for our lab. Run the installation, and while that's executing, notice how we're also installing Beautiful Soup for web scraping and the OpenAI integration through our proxy server. Once your installation completes, we explore the fundamental difference between sequential chains and stateful graphs. On the right side of your screen, you have VS Code where we'll be reviewing and running our code. Navigate to the /root/code directory and you'll see folders for each task we'll be working through. Let's start with understanding sequential versus stateful processing. Open the task2 folder, you'll see 3 Python files there. Let's look at sequentialchain.py first. This demonstrates a traditional LangChain approach. Notice how it creates an LLM instance using chat OpenAI with our proxy configuration. The chain processes 3 steps independently. It greets a person named Alice, then it says goodbye, but look closely at line 36. The farewell prompt doesn't even receive the name. Finally, it tests memory by asking what the person's name was, and predictably, it has no idea because each step is completely independent. Now open up Stateful Graph in the same folder. This is where things get interesting. Now look at how it defines a conversation state class using type dictionary starting at line 13. This state structure persists throughout the workflow. The graph has 3 nodes: greet person, say farewell, and check memory. Notice how the farewell function on line 42 can actually use the name from state. It says goodbye to Alice by name because the state is preserved. Let's run these to see the difference in action. In your terminal, execute the first script by running the Python command and specifying sequentialchain.py file. Watch the output. It processes each step independently. The greeting mentions Alice, but the farewell is generic, and when asked about the name, it has no memory. Now run the stateful graph script. See how different this is? The farewell specifically mentions Alice because the state was preserved. The memory test confirms the name is still accessible. Finally, run the comparison script to see both approaches side by side. Now let's dive into StateGraph, which is really the heart of LangGraph. Open the task3 folder and look at StateGraph_demo. This shopping cart example perfectly illustrates state persistent and accumulation. The code defines a cart state with items, total, and status fields. Watch how each node doesn't replace the state, but adds to it. The add apple function starting at line 18 takes the existing items list and adds apple to it. It doesn't replace the list, it creates a new list with the existing items plus the apple. The add banana function does the same thing, adding the accumulated state. And now run the demo. Watch the output carefully. You'll see the state grows at each step. First, the cart is empty, then it has an apple with $5 in total, then both apple and banana with an $8 total, and finally, the checkout adds a paid status. The status persisted and accumulated throughout the entire workflow. Let's explore nodes in detail. Open task 4 and examine nodes demo. The code demonstrates 4 different node types. The simple function nodes just transform data. They might uppercase text or perform calculations. LLM-powered nodes use language models to generate content or make decisions. Tool-using nodes reach out to external services like web searches or databases. Conditional nodes examine the state and decide where the workflow should go next. Now run the nodes in the demo. Each node serves a specific purpose, but they all follow the same pattern: receive state, process it according to their function, and returns updates. They're all like specialized team members, each with unique skill. For edges and routing, open task 5 and look at edge routing demo. This demonstrates how to control workflow with conditional routing. The router function examines the state and makes decisions about which path to take. Look for the add conditional edges call. This is where the intelligence happens. Based on the router's decision, the workflow follows different paths. Now let's run the demo. Watch how the workflow chooses different paths based on conditions. This conditional routing transforms a simple pipeline into an intelligent system that can adapt to different situations. Now let's explore loops and iterations. Open task 6 and examine loops_demo. The key here is the should continue function. It checks both an iterator counter and the quality score to decide whether to loop back or proceed. This prevents infinite loops while allowing iterative refinement. It's like doing research yourself. You search, evaluate what you found, and if not good enough, you search again with better keywords. Now let's run the loops in the demo. Notice how it searches, evaluates quality, and loops back if needed, up to a maximum of 3 iterations. Each iteration can be different. The search query can be refined based on what was learned previously. Tool integration is what connects your workflow to the real world. Open task 7 and look at tools_demo. The search tool node function shows how to integrate DuckDuckGo. It takes query from state, searches the web using DDGS, processes the results to extract relevant information, and adds them back to state. The beauty is that to the workflow, this tool node looks just like any other node. Watch how seamlessly external web search is integrated into the workflow. No special handling needed. It's just another node doing its job. For memory and state accumulation, open task 8 and examine memory demo. This demonstrates how state builds knowledge over time. The memory state class defines lists that accumulate data, questions, search results, key points. Each node adds these lists rather than replacing them. Now look at the accumulated pattern. It reads existing data, generates new data, combines them, and returns the accumulated result. Now let's run the memory demo. See how the knowledge builds up step by step? Questions are generated and stored. Search results are added without removing the questions. Key points are extracted and added alongside the existing data. And finally, everything is synthesized into a report while preserving all the intermediate data. Finally, let's look at the complete research assistant. Open task 9 and examine the research assistant file. This brings everything together. The research state includes all the fields we need: topic, questions, search results, findings, iteration count, quality score, and the final report. The workflow includes nodes for each step of the research processes, conditional edges for quality-based routing, and a loop that allows iterative refinement. There's also a Streamlit_app file that provides an interactive web interface. If you want to see the workflow visualized in real time, you can run this command. But let's run the command line version first. So give it a research topic and watch the entire workflow execute. You'll see it generate multiple research questions based on the topic, search for information on the question, evaluate the quality of what it found, potentially loop back with refined searches if needed, and finally synthesize everything into a comprehensive report. What you've built here is fundamentally different from simple chatbot. This assistant can adapt its approach based on what it discovers, and also refines its searches based on initial results and build comprehensive knowledge from multiple sources. Each component we explored: StateGraph for workflow management, nodes for processing, edges for routing, loops for refinement, tools for external data, and memory for accumulating knowledge, plays a crucial role in creating this intelligent system. The validation happening behind the scenes confirms each step is working correctly. You've successfully built a production-ready AI research assistant using LangGraph's powerful workflow capabilities.